Homework 6, problem 1. For a dielectric sphere with a locked-in polarization capital P of R given by KR. So it's a radially pointing polarization that's 0 in the center and grows bigger as you get further out. For these two situations, we want to find the surface charge, sigma b, the volume charge density, rho b, and we want to find the electric field everywhere for this configuration. So we'll start out. First, we'll find the surface charge, sigma b. To do that, for part A, we're going to start. Sigma b is by definition equal to n hat dot p, the polarization vector. The polarization vector is radially outward. N hat for us, in this case, is going to be simply r hat. So r hat dot r vector is just r. So this is just going to be kr evaluated at this radius, which we'll define the radius here as capital R. And so sigma b is simply k times capital R. And that's it. Okay, so that's sigma b. Now we'll find the volume charge density, rho, the definition we have for rho, right? Rho b is minus the divergence of the polarization vector. Divergence, when I look this up in the front of the book for polar coordinates, this is going to be minus 1 over r squared partial with respect to r of r squared times the r component. The r component of p is simply kr times kr. And so again, this is then the k comes out, so this is minus k over r squared, the partial derivative of r cubed, so this is 3 r cubed, and so that's going to give me that my volume charge density rho is minus 3 kr. Okay, and so that's my volume charge density and my surface charge density. Now, to find the electric field, we're going to use Gauss's law. Now, Gauss's law, if we remember, is that we draw a Gaussian surface, and so in a spherically symmetric case, we're going to draw a sphere, and the radius of the sphere is going to have radius little r. And by symmetry, and so this is for B, okay, for part B here. For B, we're writing down what we have. Gauss's law states in integral form, integral over the surface ds of the flux of E must be equal to the charge enclosed. So the charge enclosed is the integral d3x of rho. Okay. For us, all of this rho is going to be the bound charge. And so we need to go ahead and do this by symmetry, right? By symmetry, we're going to say that this E vector is only the radial component, and the n vector is itself the r hat direction. And furthermore, n hat dot E is constant over the surface. That's the real trick here. N hat dot E is constant over the surface. Doing that, the left-hand side here is going to give us the surface area at 4 pi little r squared, and epsilon naught, the radial component, the function of r. And then on the right-hand side, it's just going to be, this is constant, this is not constant inside, so I have to do the integral. And so this is, in radial coordinates, this is going to be 4 pi, the integral from 0 to r of r prime squared dr prime, and so this here is this d3x, this 4 pi r prime squared dr prime, because we don't depend upon theta or phi. So that's the d cubed x, and then we're going to have this minus 3k times r. And so we're going to be r prime. Sorry. So we're going to be integrating r prime cubed, and so here I had r cubed. I should have taken a derivative, right? So the derivative was 3r squared. So this is not going to be r, so it's not going to be r. And I'm going to be integrating r squared dr, which is going to give me 1/3 r cubed. Okay, the 1/3 is going to cancel that part there. So I get 4 pi r squared epsilon naught er of r is equal to 4 pi minus k r cubed. Okay. 4 pi's are going to cancel, and I get that the er is going to be equal to minus k over epsilon naught times r. Okay? And then to move back into the vector form, the electric field as a function of r is minus k over epsilon naught times r vector. Okay, and what we should notice, right, is this is 1 over epsilon naught times the negative of our polarization. So that's what you should find in all of these cases where locked-in polarization, where the only source of the electric field is the bound charge from polarization. You should find that the electric field is minus the polarization. So, there we go. That's the solution for part B, finding E everywhere. Oh, sorry, this is not quite true. Okay, so this is for r less than s. This is for r less than capital R. And then for r greater than capital R, the Q enclosed is 0. And so writing that, we're going to have integral over delta s d2x in hat dot epsilon naught. E is equal to Q enclosed, but we know that's 0 because I have a neutral polarization object. And so that's going to imply that E is 0 for r greater than capital R. And so now, using these two, I know that E everywhere is going to be minus k over epsilon naught r vector for r less than capital R, and 0 for r greater than capital R. Okay. And that's it. That's how we can do a locked-in problem.